One of the items listed on the previous slide that can affect the accuracy of the solution is mesh resolution. Sufficiently fine mesh resolution is needed anywhere in the domain that you have large gradients. On this slide we have an example where there's simulation of an external compressible flow past an artillery shell. The left-hand image is showing what the initial mesh looks like, and the right-hand image shows the pressure contours from the solution that was calculated on this mesh. The contours show that there's a large pressure gradient, which indicates the presence of a shock wave, but the pressure field is poorly resolved, and the wave is far too thick. In a situation like this, the grid can be adapted in regions of large pressure gradient in order to better resolve the sudden pressure rise across the shock. This slide shows what happens when solution-based mesh adaptation is used to refine the mesh based on the pressure gradient. The figure on the left shows the final mesh after a number of adaptations have been performed, and if the pressure contours on the right are compared with the grid on the left, it can be seen that with mesh adaptation, there's much better resolution of the bow shock and the expansion wave. The example on the previous two slides shows how grid adaptation can be used to improve mesh resolution locally in regions where high gradients are located. This is helpful for situations where it's difficult to determine where the grid resolution is needed ahead of time, because it allows the cells to be added to resolve the flow field without having to use a preprocessor. Adaptation proceeds in 3 steps. First, cells that satisfy the adaptation criteria must be marked and stored in a register. The term adaptation register just means a group of cells that meet a particular criterion. In the panel on the right, an adaptation register that includes all cells with a velocity gradient above a certain threshold has been marked. The register can be displayed or modified after it's marked by clicking on Manage, and is strongly recommended to display the adaptation register and make sure that the cells are what you think they are. When you're satisfied, just click on Adapt and the cells will be adapted. It's highly recommended to save the case and data files before you do the adaptation, because in theory the cells can be unadapted if anything goes wrong, but in practice it's always easier just to load the case and data file back in. Registers can be defined on gradients or ISO values of variables. They can be defined based on the proximity of cells to a boundary. They can be defined based on regions with defined shapes, such as cylinders or spheres. They can be defined based on the volumes of cells, or the volume changes between neighboring cells, and also based on the Y+ values in cells that are next to walls. To assist with the adaptation process, adaptation registers can be combined and Boolean operations can be performed. You can draw contours of adaptation function, and this can be useful if, for instance, the adaptation panel is reporting some values that you're not really sure what they mean. It can help to visualize how different values correspond to different regions in the domain. You can display the cells that are marked for adaptation, which once again is a very good idea, and in the controls panel, you can limit cells that are adapted so that cells that are smaller than a certain size are not adapted, and also that the total number of cells in the mesh doesn't exceed a certain value. In this lecture, we've discussed how to use the solvers. To summarize, the solution procedure is the same whether the pressure-based or density-based solver is used. You have to set adequate solver and solution parameters and calculate until you get a converged solution. It's recommended to obtain a solution using second-order discretization and refine the mesh and recalculate until a grid-independent solution is obtained. All solvers provide tools for judging and improving convergence and ensuring solution stability, and we've seen the most important and useful of these tools. Last but not least, just because a solution converges does not mean that it's accurate. Solution accuracy depends on mesh resolution, the use of appropriate physical models, correct boundary conditions, and a number of other factors as well. This is an important topic, and we encourage you to view Lecture 10 to learn more.